entitled Least Squares Estimation of Dynamic System Parameters Using LabVIEW, and it will be presented by Jonathan Turner.
Good morning, everybody. Like Dr. Samantha said, my name is Jonathan Turner. I'm a graduate student at Georgia Southern University in the Department of Mechanical and Electrical Engineering. And I've come here today to present a paper entitled Least Squares Estimation of Dynamic System Parameters Using LabVIEW. And in this paper, we talk about a specific application of the least squares algorithm to determine dynamic system parameters for a DC motor. And through the presentation, I want to talk about the example plant we chose for use of the algorithm, talk about how we modeled the system, and I'll briefly discuss the least squares method itself and how we implemented the algorithm. I'll also talk about the effects of noise on the ability to determine system parameters. And then finally, I'll make a comparison of the simulation of the response of the developed system with the experimental results of the response at DC motor. Okay, so first, the plant we chose to investigate the system identification technique was the Quanzer QNet DC motor control board fitted to a National Instruments Elvis 2 board for interfacing with LabVIEW. And on the right, you can see a block diagram of the scheme we used to first gather system response data. And on this slide, we'll talk about the system model a little bit. And in equation 1, you can see that the system model is the general first-order system continuous time model with parameters like steady-state gain and the system's time constant to talk about the DC motor directly. And in equation 2, we have the discrete time representation of that model, which contains parameters B1 and A1, which we'll be using the least squares algorithm to determine these parameters to describe the DC motor's dynamics for this particular plant. Equation 3 is the difference equation form of this system model, which is actually the form we will use with the least squares algorithm to determine parameters A1 and B1. Equation 4 is the vector form of that linear equation described by the difference equation. And equation 5 and 6 give definitions of the function f and theta, which contains the parameters we're trying to determine A1 and B1. Equation 7 shows that for any sample, the function f includes data from the previous samples of response data collected, including the stimulus data. And equations 8 and 9 are just vectors constructed from elements of that linear vector equation for use with the least squares algorithm. Equation 10 is that vector equation solved for the error term, which can be used to determine the sum of squares of error between the estimated system model's response and the actual DC motor's response. And that defines this function J as shown in equation 11. And when you differentiate this function J, you can determine a solution for theta as shown in equation 12. The equations on this slide show a particular iteration of the least squares algorithm for determination of theta, parameters A1 and B1. And you can see from the equations that for sample n equals 2, or the third sample gathered, you also need stimulus and response data from the second sample and the first sample to calculate parameters A1 and B1. So what this does is creates a sliding window calculation where for each 3 samples of response data, you can calculate a parameter A1 and B1 to describe the system dynamics. So throughout the range of collected data, you can calculate several versions of A1 and B1. To talk about what we did specifically, we first gathered data from the sample DC motor by providing several different input waveforms, including 0.5 hertz 3-volt peak-to-peak sine wave and 0.75 hertz version of the same sine wave, and also a triangle wave. The least squares algorithm was implemented in MATLAB and we used our response data to get some initial values for the parameters A1 and B1. These two graphs show the initial calculations of A1 and B1 over the sample range, and you can see that the least squares algorithm was unable to determine a unique value of A1 and B1 that worked over the entire set of response data. When we saw this, we created a VI in LabVIEW to do some spectral analysis on our data set, and we found that the problem was excessive noise in the higher frequency components of the data from the tachometer signal we used to gather DC motor response data. We also used this to verify that the natural frequency of our system was around 2 Hertz, and we implemented a filter accordingly to filter out the higher frequency components from our data, and retried the estimation using the least squares algorithm. When we did this, the algorithm output a very unique value across the response range for the parameter A1, which, if you'll recall, is the parameter that corresponds to the system pole locations. So that part was very certain. And however, parameter B1 in this first section, it takes a second for the value of B1 to be determined, and it oscillates for the rest of the response data over this small range of values. As you can see, it's somewhere between 6 times 10 to the negative 4 and 9 times 10 to the negative 4. So what we did is use the most frequent value for B1 to develop the system model. We actually simulated the system model we developed using the least squares algorithm, and here you can see a plot of the simulated system response compared with the actual system response by the solid line. And these are responses to the 0.5 Hertz, 3 volts peak to peak sine wave. And you can see that after the 2-second mark, sample number that corresponds to 2 seconds of the simulation, the fit is good. In the first second or so, you can see a problem with the simulation's magnitude, the magnitude of the simulation's response. And this is caused by a couple of things. There is a dead zone effect, or a presence of higher order dynamics at the actual starting time of the DC motor that the model cannot account for as we modeled it as a first order system. Also, you can see this effect in the first second of simulation. As I was talking about earlier, it takes a second for the algorithm to calculate that oscillating region of the parameter B1 value. And further along, you can see on the left, the 0.75 Hertz 3 volt peak to peak sine wave was used for the same simulation, and you get similar results for the higher frequencies, the 0.75 Hertz sine wave and the triangle wave on the right. There's slightly more phase shift caused by that initial problem with the dead zone effect, the higher order dynamics at the beginning. And you can actually see the dead zone effect more so in the actual DC motor response at the 0 point, the direction turn point. And to conclude, I want to recap what we did and what I talked about a little bit. And the first thing we did is we gathered data, or response data, from an actual DC motor, and we filtered that data to be used with the least squares algorithm and determine a mathematics model for the dynamic characteristics of this DC motor. And we implemented the least squares algorithm and evaluated the performance of the system model that we developed by comparison of the simulated response data and the actual experimental response data gathered from the DC motor. What we found on this comparison that was the best response of the simulated system was found to be for the 0.5 Hertz 3 volts peak to peak sine wave input waveform, and it came to be a correspondence of 0.15 volts, which represents 5% of the full scale input range. And that is it.